going to be available in this quarter itself, where the first solution is going to be delivered for AWS workload. So here in that solution, the multi-site orchestrator that you're using in the multi-site solution, the same orchestrator can push the ACI policies to the cloud workload as well. So if you have workload in the cloud, it can push the policies over there. And then after that, we are going to follow it up with Azure. So later half of this year, we are going to have the same solution what we are developing for AWS. We'll have the solution with Azure as well. So this is just a quick overview of how the ACI policy model has evolved over a period of time. Just a little bit more details about the ACI multipod. Though this session is not about multipods, there is a breakout session, ACI, BRKACI 2003. If you want to know details of the ACI multipod, you can go to that session or you can listen it through. In the ACI multipod solution, you can have multiple pods. And in each of these pods, you will have an independent control plane. When I say independent control plane, each pod is running ISIS, BGP, the kube. So each pod has its own control plane, and they are connected to each other by using a BGP EVPN. And using that BGP EVPN, the endpoint learning, so the servers, the VMs that are in one pod, they'll be learned in another pod. And this is a solution where you have a single epic cluster. And one epic cluster is managing multiple pods. So if you look at it from the availability zone point of view, it is a single availability zone. And in this solution, what we also do is there is a single VXLAN tunnel that gets formed across different pods. So from the data plane point of view as well, a single tunnel, right, across the pod. Of course, you have a control plane separation. So it's not a true disaster recovery solution because you are having a single management plane. This solution works when you have a 50 millisecond latency between your data center. So imagine two buildings which are closer to each other, or within the same city or nearby cities. You can use this solution and have a single epic cluster managing multiple pods. Then we had an ACI multi-site solution. ACI multi-site solution is in detail explained by Max Sardica in BRKACI 2125. In this is a two disaster recovery solution. So here you can imagine the site 1 and site 2. You can have multiple sites, and each site is running its own control plane, data plane, and management plane. Here, when I say control plane, each site is running its own ISIS, BGP, kube, and those are connected using an MPBGP EVPN session. And when I say data plane is separated, what we do here is we translate the VXLAN tunnels at the spine. So you are not having a single tunnel, and that's why it will scale much better. So it can go, with multi-pod solution, we support 400 leaf. With multi-site solution, you can go much bigger. And here, these fabrics have its own epic cluster. So you can independently upgrade, downgrade each site. And the configuration and the operations will be managed by the multi-site orchestrator, which is pushing the policies across different fabric. So this is about the multi-site solution. And in this solution, you can have the data center across the geography. You do not have a limitation of 50 milliseconds. And the reason why you don't have that is because there is no cluster which is being formed across the data centers. Because each data center has its own epic cluster. So you can go beyond 50 milliseconds, you can go up to 1 second. That's what we have tested. And when you have up to 1 second, you can essentially have your data center anywhere in the world, right? So these are like some details about the multi-pod solution and multi-site solution. So this is about the ACI policy evolution and how you can use ACI across your different data center. Now let's come to the main topic of this presentation, which is ACI remote leave. So let's take a look at the architecture of the remote leave. How does the ACI remote leave architecture work? So you put a pair of leave at a remote location. So let's say you have a branch office or some remote location, you will put a pair of leave. And the epic cluster and spines are going to remain at the main data center. So you just put only a pair of leaf. And those pair of leaf will be completely managed by the Epic cluster in the main site. So here, the Epic cluster is going to do the upgrade, downgrade, it is going to manage the policy, troubleshooting, the telemetry, all of that will be managed centrally by the Epic cluster itself, right? So you may have a multiple small data center. All of those data center can be managed centrally by the Epic cluster in the main site. Then, just like a local leaf, you can connect any type of endpoint. You can have a local L3 out. You can have a local firewall or services device connected. You can have a VMM domain with OpenStack. You can have a VMM domain with VMware. You can have a VMM domain with the containers. So you can, just like any feature that you can use for a local leaf, you can use the same features for the remote leaf as well, right? And the traffic forwarding for those endpoint, for the L3 out or for anything is going to be local. So the traffic between the remote leaf does not go to the spine in the main data center. The traffic forwarding is always local. So if you have a branch office or satellite data center, the traffic between whatever is connected in that data center is going to be locally forwarded. It doesn't go to the spine in the main data center. And we understand the remote leaf can be in a satellite data center which is connected over a WAN network, right? In that case, we cannot run multicast. So what can we do? So for multicast, VXLAN requires multicast, right? For the broadcast, unknown unicast, and multicast traffic. So we run a head-end replication so that you don't really need to have a multicast enable in your IP network. So that's the high-level architecture of the remote leaf. Now, some of the use cases that gets enabled with remote leaf. So for example, one use case that I was explaining is the satellite data center, which is like a remote data center. You have many of these remote data centers. You want to manage all of those data centers centrally from one location. Everything about those data center, the networking policies, everything. That can be done using remote leaf. You put a pair of leaf over there, don't have to put the whole fabric. You can manage those data center centrally from the main site. Then you may have a use case where you need to migrate your data center from the existing environment to the ACI environment. How do you do that? So you can put a pair of leaf, connect those pair of leaf to the remote leaf, and remote leaf will ensure you have a layer 2, layer 3 DCI, and using that, you can do your workload migration. We see a lot of customers who are using remote leaf for this purpose, migrating workload to the ACI fabric. Right? And I have some slides where I specifically talk about how simple it can make a DCI if you are using ACI and the remote leaf. If you need to migrate your workload to the to the ACI main data center, you can easily do that. Right? You may have a colo data center, and you may want to have the consistent policy across your main data center and colo data center. You can put remote leaf at the co-location and have the consistent policy. You can manage those remote leaf at a co-location centrally from the main data center itself. Then, with the 5G, what's really happening is the data center are coming closer to the user. The reason why they are coming closer to the user is because of the latency requirement. When you have gaming like AR, VR, IoT, the latency requirement are very strict, right? And or even with the vRAN, right? So there is a radio access network itself is changing. With the introduction of vRAN, the latency requirement is very, very sensitive. So the service providers are building many data centers which are closer to the users. And these data centers are typically small. They have like 2 rack, 4 rack of equipment, right? So what you can do is you can put remote leaf in those locations at the edge data center location and manage all of those edge data center centrally from one place, right? That's a huge advantage. Otherwise, imagine you have to manage so many individual switches, upgrade, downgrade, configure, all of that. Here, you are doing it from one place, one Epic controller. All right? So these are some of the use cases of the remote leaf. Now, what is the hardware and the software which is required if you want to run it? So the hardware which is required is the next generation leaf and the spine. So if you have EX or later, you can use remote leaf. Now, why? I will explain you in one of the slides. Why we need a next generation, why it will not work with the first generation spine. And the software requirement is ACI 3.1.1. So it has been shipping for over a year. So in last December, in 2017, that's when we released it. Last December is not just 1 month away. It's like 1 year and 1 month away. Yeah? And then what we recommend you to always do with the remote leaf is put the remote leaf switches as part of the VPC domain. Okay? So you can connect the endpoint by using VPC. You can connect the endpoint by using active-active, active-standby. All of that works, right? Or orphan port. But connect the remote leaf switches as part of the VPC domain. If you have a pair, just connect them as part of the VPC domain. Why do we recommend that? Is because there will be a control plane session that will be formed over the upstream router. So you see the upstream router over there? There will be a VPC control plane over that router will be formed. And using that VPC control plane, we are going to learn the endpoint information. And since we can learn the endpoint information, I can forward the traffic locally. I don't have to go back to the spine in the main data center and come back, right? So that's precisely what we do over here. So if you look at it, in the next slide, I'm just talking about that, right? If you have a VPC domain, then you have an endpoint 1, endpoint 2. They can talk to each other directly over, directly from the remote leaf itself, because endpoint 1 and endpoint 2 both are learned on the remote leaf switches, right? So there will be a direct traffic forwarding. Even for an orphan port, right, or a non-VPC connection, the traffic will go to the upstream router and come back. So it is not really going to the spines in the main data center. The traffic forwarding is still local, right, the site local. Now, this was about the high-level use cases and how do you connect the endpoint and really how the traffic forwarding works, right, at a high level. Let's go a little bit deep and see what are the requirements. What are the requirements from the IP network point of view for the remote leaf? And how does the discovery works, right? Is it the same experience as what you see with the local leaf, right? The local leaf gets discovered automatically. Will the remote leaf will get discovered automatically as well? So let's take a look at that. With respect to the network reachability requirements, so remote leaf switches will need a TEP pool. So there is going to be a TEP address that will be required for the remote leaf. So TEP address is nothing but the VXLAN tunnel encapsulation and decapsulation. That's where the VXLAN, all that magic really happens. And then there is a TEP pool which you give it for the main data center, right? So you give the TEP pool for the main data center, you give the TEP pool for the remote leaf switches. So in principle, the remote leaf switches are basically part of the pod itself. So they get logically associated to one of the pod. Now, if a switch is logically connected to one of the pod, naturally the requirement would be that you need to have the TEP pool reachability from the pod where it is associated to, right? So you need to make sure that you have the TEP pool reachability, the main data center pod's TEP pool is reachable from the remote leaf. And from the discovery point of view, the epic controller infrastructure IP address should be reachable as well. So from the remote location, you need to make sure you have a reachability to the TEP pool of the main data center, and you also have a reachability to the epic controller's IP address. And at the main data center, you just need to make sure the TEP pool of the remote leaf is reachable from the main data center. So you need to make sure that these two are reachable to each other. You could have a routable TEP addresses, or you may have a VRF extended, or make sure that there is a logical connection between these. So in terms of the latency and the bandwidth requirement, how far a remote leaf can go from my main data center. So we have a reachable, from the latency point of view, it can be 300 millisecond away from the main data center. And the bandwidth requirement is 100 Mbps. So I get asked a lot of time the question, why 100 Mbps, right? Will it not work if I have 50 Mbps, some say 10 Mbps, right? So that kind of question always comes up, why? So the reason why we have 100 Mbps is, imagine you will have some kind of a control plane, which is going to the main data center. You may have some cases where, when you want to do an upgrade, downgrade, you want to download the image. So we have kept a minimum of 100 Mbps for that purpose. You will see that most of the time, the traffic forwarding is local. In fact, now I will share, like almost all the time, the traffic forwarding is local, but still, there will be some situations where, like when we support, multi-site, there will be some cases where the traffic is going to the spine, and I'll talk about those cases. So the requirement today is 100 Mbps. Will it work with the lower bandwidth as well? Probably yes. But what our validation within the BU has happened is with the 100 Mbps. Yeah? Now, the MTU requirement. Since I said that the remote leaf switch is part of the same fabric, and within the fabric, we run VXLAN. So the remote leaf switches are running VXLAN with the spine in the main data center. And since we are running VXLAN, you need to make sure you have 50 or 54 byte extra MTU than your application requirement or your endpoint requirement. But what about the control? The data plane is solved, but ACI fabric is running the BGP protocol, COOP protocol, and what if the MTU in your network is not 9,000, right? If it is 1,500, in that case, what we recommend you to do is lower the control plane MTU. And this is where you see the setting to lower the control plane MTU. What it will do is the control plane MTU of the BGP packet, of the COOP packet, is never going to exceed this value. So for example, let's say you have a 1,500 MTU in your network, right, IP network. You can adjust this value to 1,450. Right? So the ACI control plane packet are never going to exceed beyond 1450, so you are covered, right? When the VXLAN header is getting added, you're covered, right? So this is what this setting will do. So these were the requirement from the IP network point of view. Now the discovery. So when the typical, expectation is someone is going to a remote site, power on the switches, and they'll be discovered in the fabric. That's the expectation, fair expectation, because that's how today, if you look at the ACI leaf switches, you power them on, and they will get discovered, right, automatically. So that's precisely how the remote leaf discovery works as well. There are two pieces of the discovery process for remote leaf. One is the IP address assignment for the uplink interfaces. So remote leaf will have uplink interfaces to the upstream router. So you see, these are the uplink IP address, uplink interfaces which are connected to the upstream router. So first, the uplink address for the remote leaf will be assigned, and after that, the tunnel encapsulation, so TEP address will be assigned to the remote leaf. So let's see how does that work. So when the remote leaf boots up, when let's say the network admin or operator has gone in and installed the device, after that, it will just power it on. When the remote leaf is getting powered on, it is going to send a DHCP discovery message. That DHCP discovery message will have a uplink interface information. And that DHCP discovery message goes to the upstream router, and on the upstream router, you would configure a DHCP relay, the OSPF, and a subinterface with VLAN 4. Why subinterface with VLAN 4? Is because the DHCP discovery message is coming with the VLAN 4. So you configure this on an upstream router and make sure there is a reachability to the Epic controller. So the DHCP discovery message will be relayed to the Epic controller. Now, Epic controller, understand I got a DHCP discovery message with this uplink interface information. So let me respond with the DHCP offer, and I'll give you, and it also gives the DHCP, it also gives the bootstrap file location. After that, the DHCP request will be sent from the remote leaf, and Epic controller is going to do a DHCP acknowledgement. You don't have to do anything. You just powered it on. This process is going to happen, and the uplink IP address will be assigned on the remote leaf interfaces, right? So the uplink IP address assignment is done. After that, the TAP IP address will be allocated. And the same process follows. So remote leaf is going to do a DHCP discovery, and this time it is doing it for the TAP addresses. The DHCP message is relayed to the Epic controller. Epic controller replies with the DHCP offer. There is going to be a request from the remote leaf for the TAP address, and there is going to be acknowledgement. After this process is done, it is completely discovered in the fabric, and it's going to look something like this. So the operator goes, it puts in the remote leaf switches. All of this magic is going to happen, and then the remote leaf will be discovered just like any other leaf in the fabric. So as you can see, this is a snapshot from my lab where you see the remote leaf switches as 2. So the remote leaf is discovered, and it is going to look like this, right? That it is connected over a WAN network. Now, once this process is completed, you can do pretty much everything that you can do with the local leaf, right? So you can upgrade, downgrade, push the policies, configure it in a EPG where local leaf is connected, all of that, right? So it is going to work exactly in the same way as a local leaf. When this process is done, your DCI connectivity is already established, right? Because the remote leaf and the main data center are connected now. All right. So let's take a look at what is the configuration that you need to do on the upstream router, which is connected to the remote leaf. This is for your information. What you really need to do is configure a subinterface with VLAN 4, enable OSPF, and then configure a DHCP relay, right? Then what is the configuration that you need to do on the upstream router which is connected to the spine? All that you got to do is enable a subinterface and configure a OSPF, right? So this is a sample configuration from the Nexus 9K devices that I had. This is going to be more or less same configuration on most of the devices. So this was about how does the remote leaf discovery happens, right? What is the IP network requirement for the remote leaf switches? Now let's take a look at a control plane and data plane learning, right? How does the control plane learning happens? How does the data plane forwarding happens? Let's take a look at that. So as I mentioned, the TAP address will be allocated for remote leaf switches. So every remote leaf is going to have a TAP address. It is, we are calling it as data plane TAP address. So you will have a data plane TAP address which is allocated to every remote leaf. And then we will also have one Anycast TAP address. Why Anycast TAP address? Is because they are part of the VPC domain. So there is going to be an Anycast TAP address. So the packet from the spine can be received by any of the RL, and it is still going to do a local packet forwarding, right? So there is going to be an Anycast TAP address as well, which is on each of these remote leaf. Then from the main data center pool, there is going to be a TAP address that will be assigned for spines. We call it as an Anycast IP address. Why we give this Anycast IP address? Because when the packet is coming from remote leaf, any spine can actually process that packet, right? So we give an Anycast IP address for unicast traffic, and we give an Anycast IP address for multicast traffic. So these are the TAP addresses that will be allocated to the spine in the main data center for remote leaf switches, and remote leaf will have also TAP addresses which will be assigned. Now let's take a look at how the endpoint learning happens. As I mentioned before, the remote leaf switch is like an extension to the pod, right? So within the pod, we run a COOP protocol. And the COOP protocol is used for endpoint learning, right? So we run a COOP protocol between the remote leaf switches and the spine in the main data center, and using that, the endpoint information will be learned between remote leaf and the ACI in the main data center. So here is an example. So endpoint 3 is connected to the ACI in main data center, and you see endpoint 1 and endpoint 2 are connected at a remote location. So using the COOP, we will have this information. The main data center is going to learn endpoint 1 and endpoint 2, and remote location data center is going to learn endpoint 3. If you notice, the endpoint 1 is learned with the Anycast IP address of the remote leaf switches, right? Because it is connected in a VPC fashion. So the packet can go to any of the remote leaf. While endpoint 2 is learned on the main data center by using a data plane tap of the remote leaf 2, because it is connected in an orphan port fashion. So it will directly go to the leaf where it is connected. And endpoint 3 over here, which is in the main data center, is learned with the Anycast IP address of the spine, which means it can go to any of the spine. So this is how really the learning happens, the control plane learning between the ACI main data center and the remote leaf switches. So this is about the control plane. Let's take a look at the data plane. So with respect to the data plane, let's say the endpoint 3 in the ACI main data center needs to talk to endpoint 1 in the remote location. So what will happen in this case is the endpoint 3 is going to send a packet to the endpoint 1 with the source IP of it himself and the destination IP of endpoint 1. This packet will come to the leaf 4, and the leaf 4 is going to encapsulate this packet into VXLAN, right? Within the ACI, we are running VXLAN. So this packet is going to get encapsulated at leaf 4 in the main data center. And the tunnel endpoint address at this point in time is going to be, the source address is going to be the leaf 4 tap address. The leaf 4 is the source, so it is going to put its own IP address as a tap address. And the destination at this point in time is going to be the Anycast IP address of the remote leaf switches, so that it can directly go to any of these remote leaf switches. When this packet comes to the spine rewrites the source tap address so that the packets can come to the spine, right? So the spine does this rewrite, and it will update the source IP to the Anycast IP address of the spine. And this rewrite mechanism is not available on the first generation spine. That's why you need a next generation spine, all right? So the spine updates the source tap address to the Anycast IP address of the spine. And at this point in time, the spine will also learn about the endpoint 3. It will know that I learned this packet with the source tap of the L4, which is the leaf 4 tap address. So spine is going to learn the endpoint 3 information, and it also changes the source tap. When this packet comes to the remote leaf switch, the remote leaf switch is going to learn the endpoint 3 information with the Anycast IP address of the spine. Why? Because that is the source tap. That spine changed it, right? So the endpoint 3 information is learned on the remote leaf, and after that, the remote leaf is going to remove the VXLAN header, and it is going to de-encapsulate and send the packet to the endpoint 1 because it is directly attached to it. So the endpoint 3 learning has happened on the remote leaf. It has happened on the spine in the main data center. So now, when the packet from the endpoint 1 needs to go to endpoint 3, first a normal IP packet with the source IP address of endpoint 1, destination IP address of endpoint 3, the remote leaf is going to encapsulate this packet, and it will encapsulate with the source IP address of itself, which is Anycast IP address of the remote leaf switches. And then the destination is going to be the remote leaf ucast tap or Anycast IP address of the spine, because that's what is there in its hardware table, right? So the packet comes to the spine in the main data center, and what is spine going to do? This packet is meant for the spine. It removes the destination IP address, it knows that the endpoint 3 is reachable via layer L4 TEP address or the L4 leaf. So it is going to remove the destination IP address and it's going to send this packet to the leaf 4, and the leaf 4 now will de-encapsulate the VXLAN header and send it to the endpoint 3. So this is how the data plane is going to work when the packet is being sent from remote leaf switches to the local leaf switches, or from the remote location to the ACI main data center. Now let's take a look at when I say you can extend the policy from the remote location to the main data center. How do you really do that? So one example of this is this from my lab, where you can see there is a EPG, EPG1, and this EPG has the virtual machine from main data center and remote location data center. So essentially, as long as you do this, the L2 stretch is done, right? Because now you have within one EPG and BD, you have the endpoint from both main data center and the remote data center. So this is how you can simply stretch your EPG and the bridge domain. So this is like very, very simple way of building a stretch or a policy extension from main data center to the remote locations. That's about it. There's nothing else that you really need to do for this. And let's say you want to do a VM mobility. So essentially, let's say you have an environment where you have a VLAN 100 and a gateway IP address of 100.1.1. And there is a contract and there is an ACI policy, right? When this VM moves to the main data center, automatically the policy will also move to the main data center. You don't have to do anything else. The policy will automatically move to the main data center switches wherever this VM has migrated to. If it migrates back to the remote leaf, the policy will migrate as well. So essentially, that's precisely how it really works. So this is how you can move your workload, and the policy will move as well, right? So this is what we call it as a policy extension to the remote data center. Any questions so far? Sure. Yes. So I have a slide on that. So the question, today the question is there a limit of number of remote leaf that I can have? So today it is 20 pairs, which is we are supporting since FCS, which is like 40 leaf or 20 sites. But we are increasing it to 64 pair in ACI 4.1 release, which is like 128 leaf. And this is going to be released in Q1, Q2 of this year. And then we also have a plan to increase that limit to 120 pairs, right? So yes. Yes. So the question is, can I have more than a pair of leaf at a satellite location? Answer is yes and no. The reason is you can have, and I have a slide on that, how you can actually make it work. But the recommendation would be, if you have like 4 leaf, you may want to go with the ACI mini fabric, where you have like 1 Epic controller or maybe 2 VMs. But yes, you can do that, and I'll explain it. And you may want to have a local forwarding, right? You don't want to go, exactly. I have a slide on that. I'm going to cover that. Yes? Back-to-back connection between the leaf and the spine? Yeah. I mean, the question is, can I have the back-to-back connection between the remote leaf to the spine directly? If you have that connection, that is like a single fabric, right? You can, I mean, that leaf is not a remote leaf. It is like a local leaf itself. So that will work anyways. Yes. All right. So that is what you asked is the next section, where how does it really work? So when you have multiple remote leaf pairs, right? So you have, let's say, 2 locations, or within one location itself, you have 2 pair. Now today, the traffic goes back to the spine and comes into the main data center, right? That's how it works today, okay? And the reason for that is simple, right? Because between the two remote leaf, if it is part of the same pod, then the traffic always goes to the spine and comes back, right? So this is how this solution was developed. But we have friends like who are our customers as well, who ask that, you know what, oh, it doesn't work for me. What you need to do is do a local forwarding. In some cases, I may have 4 leaf, right? Or some cases, I may have different location itself, and I would not want my traffic to go back to the spine and come to the main, go back to the spine and go to the other location. Yeah, fair ask, fair requirement, and that's where it is, right? So in ACI 4.1.2, which is going to be the Q2 of this year, you can have a local forwarding across the remote leaf pair. So the traffic will not go back to the spine in the main data center and come back. So here in this example, you can see the left pair, which is blue pod, I would say. There are 2 locations. And similarly, there is an orange pod and 2 locations. The traffic can be directly forwarded between those remote locations. How are we making it work? So we build a VXLAN tunnels. We build a VXLAN tunnels across the remote leaf pair, right? And we also learn the endpoint information wherever endpoint, so we don't blindly build tunnels everywhere, right? So wherever there is a communication which is happening, we will build the tunnel on demand. And we will also learn wherever the communication is happening, we will dynamically learn those endpoint information into the hardware table so that we can forward the traffic directly over those VXLAN tunnels. So we are going to build the tunnels over here, right? And so that the traffic can be directly forwarded across remote leaf pairs. Now this is one case where you see the traffic is directly forwarded within the pod. But the same solution is going to work across the pod as well. So let's say you have multiple pods. You have a multi-pod solution. And you want to send the traffic from one remote leaf location to another remote leaf location. And these are in different pods. The traffic is going to get forwarded across remote leaf pair as well, which are in different pod directly. How are we going to do it? The same model. We build a VXLAN tunnels, and we also learn the endpoint information, which is across the pods, right? Or across the remote leaf pairs, which are in different pod. So that's how it is working, right? But all of this works when you have within one site, right? When you have within one site, when I say epic controller domain. When you are across site, you may not want to do that. And the reason for that is you may not want to have so many tunnels going across different sites, right? So you want to have it more scalable architecture. That's why we don't build the site. That's why we don't build the tunnels across site, right? So in a case of multi-site, the traffic will go to one of the spine wherever the remote leaf is logically associated to, and then from there on, the traffic will be forwarded, right? So this is how it is going to work when you have a multi-site solution. So while developing this, we were talking to the customers as well, right? How it should really be. And when we were discussing this, we learned that in most of the cases, the branch office, when you have to go really across site, the fiber connections are from a central location. So you don't really have a fiber connectivity from everywhere, right? So it is okay when the traffic has to go across site, it can go to a central location. But within the pod, it is going to be a directly traffic forwarding. Yeah? Did it answer your question? Oh, thank you. Yes. So now let's take a look at how are we making it work, right? And this time, I'm giving you just a brief information about it. Maybe if we have this session next time, I will tell you a little bit more detail about how it is really working, but just a brief information about it. So what we are doing to make this work is we are building a software database on the remote leaf switches. And this software database is going to have endpoint information of all the bridge domains and the VRF, that are deployed on the remote leaf. So it is not syncing all the information. Whatever bridge domain and VRF that the remote leaf is configured it will get that information from the main data center spines and locally put it into a software database. Still, we are not using a hardware table. It's still there in the software database, right? And then when remote leaf needs to send a packet out, it is going to first take a look at the software database and will see, do you have this entry? And when it is communicating, at that point in time, it is downloading this into the hardware table. If the software database has that entry, it is going to download that into the hardware table and then forward the packet. But what if the software database does not have this entry? In that case, it is going to check its local, it is going to send a glean packet, and this glean packet is basically sent to discover the endpoint. So it is going to check, do I have this endpoint locally connected to me, which has been silent and never responded, right, or never communicated. So it is going to send that glean packet, we'll check it locally. And it'll also send one glean packet to the spine and say, can you check it? Can you check it in that bridge domain if there is any particular, endpoint which is there, right? So it is going to check the spine and check it locally. If that particular endpoint is found, the COOP will get updated. Since the COOP is updated, then the remote leaf software database will get updated, and the hardware table is going to get updated. So this is how we are making sure that the solution is scalable. It is building the tunnel. It is learning only when it is required. And the tunnels will also get formed only when there is a communication, otherwise not, right? So this is how we are making it a scalable solution, yet there is going to be a direct traffic forwarding. Sure. Yeah, I have a slide on that, right? So multi-site and remote leaf are not supported today. It is going to be supported in ACI 4.2 release, right? But it is not supported today. I would have written that. Yeah, it's incorrect. 4.2. Sorry, that's my mistake. It's 4.2, right? Which is going to be Q2. The time frame is almost going to be the same, right? 4.1.2 and 4.2 both are going to come in the Q2, right? So time frame is wise, it is same, but I will change the slide as well. When it is going to be reposted, I will change this entry to 4.2, although the time is same. All right, now let's take a look at how the external connectivity works when you have L3 out at remote leaf and you have a L3 out in the main data center. And both L3 out in the main data center and the remote leaf can learn the same prefix, right? So for example, in this case, there's an external client 2020.21, which is from the subnet 2020.20/24. The remote leaf is learning this prefix using a locally directly connected interface, right? So remote leaf is learning this prefix locally. It is going to prefer that local route, right? And the main data center is learning this endpoint information, or sorry, this prefix information locally. So the main data center is going to prefer the local VTAP, right? So the local border leaf tap address, it is going to prefer that. Since the remote leaf is part of the main data center pod itself, there is going to be a BGP EVPN session as well. From that session, the main data center will also learn the prefix with the remote leaf tap addresses, right? And similarly, the remote leaf is going to learn these prefixes from border leaf tap because there is a BGP session that is running. But remote leaf will always prefer the local prefix because it is coming from the direct L3 out. Similarly, the main data center is going to prefer the prefix which is learned from the border leaf tap addresses because the ISI metric for the remote leaf tap addresses is going to be higher. So the traffic forwarding in the outbound direction will always be local. right? So if you have the same prefix that is learned from local L3 out versus the L3 out from the other direction or the other pod or from the remote leaf L3 out, it always prefers the local L3 out, right? So the traffic is always locally forwarded. Now, since there is a backup path, right? So if the local L3 out fails, it can always go over and send the traffic from the main data center. If the local L3 out at remote leaf fails, the traffic can be forwarded from the main data center L3 out. Similarly, if the local L3 out and the main data center fails, traffic can get forwarded from the remote leaf L3 out, right? So there's always a backup path. Now, let's say you have stretched a BD and EPG, the example that I was showing you before. So what happens in that case is both the layer 3 out are going to advertise the subnet route. So imagine a EPG which is let's say from a BD 100.111.0/24, that's the subnet, right, for that EPG or bridge domain. Both L3 out are going to advertise the same prefix, the same subnet. So while the outbound traffic is local, the inbound traffic can come from a different direction because it's a ECMP. Both L3 out, remote leaf L3 out, and local L3 out in the main data center, both are advertising the same prefix. So from the WAN, traffic can come from other direction. And it is going to make the life interesting, right? If you have a firewall deployed, it's going to drop the packet. You need the symmetry. So for that, what you can do is you can advertise the host routes from both remote leaf as well as main data center. So you can advertise the host route. When you are advertising the host route, it will come directly to the individual host. So if for the endpoint which is sitting in the main data center, it will go to the main data center. For the endpoint which is sitting at a remote location, the traffic will go to endpoint which is sitting in the remote location, right? So it's always going to be, the path is always going to be symmetry. But let's say you have a case where most of your endpoints are in the main data center. Only few endpoint, or for migration, you have few endpoint at a remote location. In that case, you don't want to burden the WAN with so many host routes, right? Most of my endpoint are sitting in the main data center, and there are only few in the remote location. So what I can do is I can have a subnet route being advertised from main data center and host route advertised from remote location. In this case, what is going to happen is most of the traffic is going to come to the main data center, and only the specific prefixes or a specific endpoint traffic is going to come to the remote location. So the problem of too many host routes can be solved in this way, right? When you have endpoint which are mostly in the main data center part. All right? So this is how the external connectivity works for remote leaf. Now let's take an example of, I've been saying, you can do a migration using remote leaf. It's a simple L2, L3 DCI. So how does that really work? So what you can do is, let's say you have a brownfield environment. You have VLAN 100, right? That needs to go to the main data center, which is ACI-based data center. So what you can do is you can connect your brownfield environment to the remote leaf. So connect the ports from your brownfield data center to the remote leaf switches. And as soon as you do that, the L2 DCI or L3 DCI is connected, right? Pretty much done, because now when the endpoint move from the brownfield environment to the main data center environment, the gateway is going to move, the policy is going to move, everything is going to move automatically as soon as you add those ports in the main data center. So it's one of the simplest form of the data center interconnect when you use remote leaf with ACI. And you're using the same technology. You're using data center is built with the ACI, and the DCI is also ACI in this case. You can do a workload migration because now you have a layer 2 connect. It's a So it's a consistent gateway. For example, the gateway here in the brownfield environment will when the endpoints are in the brownfield environment, the gateway is sitting on the remote leaf. It can sit outside of the remote leaf as well. If you make the EPG as L2 EPG or L2 L2 BD, and when the endpoints are connected in a brownfield environment, the gateway is sitting on a remote leaf. When the endpoint moves to the ACI main data center, the gateway will automatically move to the ACI main data center as well. And you have a consistent policy. Whatever you have defined for your main data center, that's the same policy for your remote data center as well. And let's see it how. So let's take an example of, let's say you have a data center which is built with Nexus 2K, 5K, 7K, or with whatever switches, right, that you have. What you can do is, let's say you have a VLAN 100, right? I'm just picking an example of VLAN 100 here. So you have a VLAN 100. Attach ports from VLAN 100 to the remote leaf switches and create an endpoint group. And this endpoint group is, and add the static port into the endpoint group, whatever interfaces that you have added from the brownfield environment, put them into an endpoint group. And that's with VLAN 100, and put the gateway IP address of your brownfield environment onto the bridge domain. And now, when you are moving your ports from the brownfield environment to the main data center environment, add those ports in the main data center, and you are done. Just add the ports. Initially, you had the ports from the brownfield environment. When those workload goes into the EPG in the main data center, you add the port over there, and it's done. If you want to have a gateway outside of the ACI fabric, that's possible as well. What you need to do in that case is initially make the ACI bridge domain as L2, and then you can migrate the gateway on the ACI later, right? So this is nothing but like a migration from using ACI, right? It becomes really simple, and I know a lot of customers, including in Europe, are actually using remote leaf in this fashion for their migration purpose. Now, there are some consideration for this, right? What are the consideration? I would say don't create a loop. That's the thing, right? Don't have a backdoor path connected between your main data center and a remote location. How can you, because the ACI fabric is not going to transport the bridge domain BPDUs, the ACI fabric is not going to transfer the BPDUs across the remote location and the main data center. Ensure that there's no backdoor path, and the spanning tree route is outside of the ACI fabric, right? So just make sure you don't do that. Now, let's take a look at how the failures are handled, right? When you have failures, what really happens? So for example, when your Epic controller fails, we know that there is not going to be any impact on the data path, because the Epic controller is not really there into the control plane or into the management plane. So if Epic controller fails, the traffic forwarding is going to continue to work. What is going to happen in this case is, of course, you cannot provision the remote leaf switches because the Epic controller is gone. You cannot rediscover or you cannot add more remote leaf switches because the Epic controller is not there. But the traffic forwarding will continue to work. Now, a lot of people ask this question, what if my main data center is gone, the spine has failed, the IPN connectivity is lost, what do I do in that case? So the local forwarding will continue to work in that case as well, right? And when we initially released it, the new endpoint discovery for when the bridge domain was in a proxy mode, it was dependent on the spine. Now we added a new process that we call as T-glean process that will ensure that the new endpoint can be learned as well, right? And traffic forwarding locally will continue to work seamlessly, no problem with that. So if the spine Epic controller has gone down, this remote data center will continue to work. But what will happen to the other traffic, right? And we will come to that as well. But before I go there, what if all the uplink interfaces of the remote leaf has gone down, right? In that case, the remote leaf will bring down its downlink interfaces as well, and the traffic forwarding can still, the endpoint will detect it and it will switch to alternative path, right? Now, what if all the spines in the main data center pod has failed? And this is where in ACI 4.2, when we have this RL direct feature, it is going to be very helpful. Right, sorry, ACI 4.1.2 is RL direct coming. 4.2, almost similar time frame. That's when the spine failure cases will be handled. Now, what really happens? Let's say the spine in the main data center has failed. Right, all the spines have failed. So what remote leaf switch is going to do is, it is going to have a COOP session with the alternative available spine in the same fabric. So if you have a multi-pod solution, one pod spine has failed, it is going to have a temporary few seconds of traffic loss, maybe 1 second, or still working out. Most likely it is going to be sub-second, but maybe 2-3 seconds, right? And then what is going to happen is, it is going to build a new COOP adjacency with the alternative available spine, and then the traffic forwarding, the new endpoint learning, all of that control plane will work, right? And when the spine fails in the logical, wherever the remote leaf was associated to, it is going to pick the alternative spine for the control plane, and the data plane was anyways direct, right? So the data plane will continue to work directly. For the control plane session, it will build a new session with the alternative available spine for the COOP. Similarly, for the BGP, right, that's where it learns all the prefix information. So it is going to build a BGP session, BGP route reflector session with the alternative spine as well. So your traffic forwarding will continue to work, right, and it's going to be direct when the spine fails in its logically associated pod. Yeah? Now, what happens? Oh, this is where I was correct, right? ACI 4.2. The previous one, I missed it, right? So, so remote leaf with ACI multi-site in 4.2. When the spine, let's say you have a multi-pod, right? So the traffic is still going to work. It's just that there is going to be a logical association from the control plane point of view to an alternative spine. And the traffic will go to the spine wherever it is logically associated to, and then it will get forwarded outside. As I said, in case of multi-site, the traffic still goes to the spine, and from there it takes out, right? So that's precisely how it is going to work when you have a spine failure in an ACI multi-site and remote leaf solution. Now, let's say you don't have a multi-pod solution, so you don't have really alternative spines, right? What happens in that case? So in that case as well, the local traffic forwarding will continue to work, right? No problem with that. And the endpoints which are learned and the communication is still happening will be directly forwarded, right? Because the communication is still happening, the endpoints across the remote leaves is not timed out. So I still have the hardware entries, I still have the software database, I will continue to forward the traffic, right? But if the connection is timed out, there is not going to be a new endpoint learning because the COOP is gone, right? So I cannot learn the new endpoint across the remote leaf switches. So that is not going to work. What is also not going to work is, since the spines are down, the BGP session is going to be down as well, and the external endpoint with the external prefixes coming from remote leaf pair 1 to remote leaf pair 2 is not going to work because the BGP sessions are down, right? The BGP session, the spines are acting as a route reflector, that session is down. So the traffic for the external prefixes is not going to work. So that's precisely what is going to happen if you have a single pod. So if you want a true redundancy, have a multi-pod solution with remote leaf, right? Otherwise, it will work in the traffic, the endpoint traffic is going to continue to work, and have even with single pod, losing all the spine is a bigger failure, right? I mean, your main data center is completely down, so you need to be looking at that as well. Of course, you want to have a traffic forwarding from remote leaf point of view, but having all spine down is a catastrophic event in itself, right? Now, some best practice and recommendation for remote leaf deployment. Let's take a look at that. So, you may have a situation where you may not find the upstream router is expensive, you don't have 40 gig, 100 gig port, you have only 1 gig, 10 gig ports on the upstream router, right? So, how do you make it work? So, what you can do in that case is you have a QSA, put that onto the upstream interfaces of the remote leaf and connect to the upstream router, which could be, let's say, ASR1K or any other router, right, for that matter. You may not have 40 gig or 100 gig links available at those remote locations. You can use QSA for that purpose. Now, you may have started with the first generation spines, right, and the fabric is already built up. First generation spines are working perfectly okay. Now, for the remote leaf, you need a next generation spine. How do you make it work? So, what you can do is you can have a mix of first generation and second generation spine in your main data center, right. So you add more capacity into the fabric by connecting those next generation spine into the fabric, and to make the remote leaf work, you always connect the spines which are remote leaf capable or the second generation spine to the IP network, right. That is something that you need to do to make the remote leaf work. Now, QoS recommendation. So, within the fabric, you have COS3, which is your control plane traffic, policy plane traffic, COS5 for the control plane traffic, the span and trace route. So, there are cost setting which is by default within the fabric. And since within the fabric the traffic is not going anywhere out, it is already taken care of, right. And between the leaf and the spine, we give appropriate priority and all that is taken care of. But when you have remote leaf which is connected out somewhere at a remote location, you need to make sure you appropriately prioritize your traffic. So, you prioritize your control plane traffic. So, COS5 traffic, you prioritize it. COS3 traffic, you prioritize it. COS6, which is trace route traffic, you prioritize that in your IP network. You may want to deprioritize your span traffic, right. So, do appropriate cost settings in your IP network, because if remote leaf has to continue to function, you need to make sure that the control plane traffic is not dropped, right. Policy plane traffic is not dropped. So, just do that cost setting. I mean, this is something, this is the best practice, right. Now, PBR, and there are a lot of improvement that we did in ACI 4.0 to make sure the traffic does not go to the spine in any case, right. So, PBR traffic, today if you look at it, our existing ACI main data center, the PBR traffic always goes to the spine. We do not do an endpoint learning, and that is why the traffic always goes to the spine and come back. In a local leaf, it is okay because it is within the fabric, but when it comes to the remote leaf, not okay. The PBR traffic has to be locally forwarded, right. Traffic should not cross the IP network or WAN network, because WAN is very expensive. So, in ACI 4.0, the PBR traffic is locally forwarded. So, we learn the endpoint information on the remote leaf switches, and the traffic is locally forwarded, right. It does not go to the spine in the main data center. Now, the inter-VRF traffic, today if you look at it on the ACI main data center, the inter-VRF traffic always goes to the spine and come back. You probably would not even notice it, right. Within the same fabric, I do not care, I have 100 gig link, 40 gig link, it is okay, right. Not okay when you have a remote leaf, right, because it's going to cross the WAN bandwidth. So, in that case, we still do a local packet forwarding. Oh, it is still going to the upstream router, and that is not because I had incorrectly drawn that link. It actually goes to the upstream router, right. So, it goes to the upstream router and come back. Now, you may ask a question, why do you send it to the upstream router as well? Why can't you locally forward it? So, when you have an inter-VRF, when the packet for endpoint 1, which is there in VRF1, it needs to send a packet to the endpoint 2, which is in a different VRF, we do not have the policy information. So the policy information of VRF2 is not available in VRF1. So we need to recirculate the packet. So what we do over here is we build a recirculation tunnel, and the packet goes to the upstream router and come back, right? Because of the policy plane. Of course, from the routing plane, we can do the route exchange within VRF. From the policy plane point of view, we send the traffic first in a different, and when it comes back, it lands into a different VRF. So the traffic goes to the upstream router and comes back. The scale, right? You had asked a question on the scale. So today we support 20 pairs in ACI 3.1. In ACI 4.1, we are going to support 64 pair, and this is going to be like Q1, Q2 of this year. And we have a roadmap to support 120 pairs of remote leaf per site. Now, if you need more scale, you can build multiple sites, right? So if you want more than 120 pairs, you can build multiple sites, and then you can get more scale. With respect to the feature and the scale, so let's say you may have a question, how many endpoints are supported on remote leaf, how many bridge domain, how many contracts, all of that is same as local leaf. So you don't have to look into the configuration guides because this information is not there because it's not required, right? It's the same scale that you have for a local leaf. Now, one thing to remember over here is, let's say you have a pod, and in that pod, you already have 100 local leaf. And Sonu said, I can do 64 pairs of remote leaf over here. So I will put 64 remote leaf, and I have 100 local leaf, and the overall pod scale is only 200. You reach to 228. So remote leaf scale is counted in overall pod scale. It is not that you can have 200 local leaf, and then you can add 64 remote leaf as well. No, right? So that's not supported. It is counted as the overall leaf scale, right? Same thing for multi-pod as well. Multi-pod, you have a 400 leaf limit. It is remote leaf will be counted in the overall scale of the fabric, right? Now the configuration and verification. This is something which is, I was very, very particular with, right? When we started with remote leaf, I mean, there are many features where you have to configure, on one page something, then second page something, and then you miss something, right? And then you break your head for 2 days and say, missed it. It was such a simple thing. I could have gone to that page and click on this knob. We don't want to do that for remote leaf, right? When we were building it, make sure you have one single page where you can do everything. So we built this wizard. I'll say 100% time, unless you are doing it programmatically, right? You are using APIs. That's different. But if you are configuring it using GUI, 100% time, you should use this wizard. Absolutely. I mean, this will make your life simple, right? So what you do here is you need to, when you configure a remote leaf, you need to pick which pod the remote leaf is going to be. You need to pick a remote leaf tep pool, which you can configure from here itself. You need to pick what is the prefix range between the remote leaf to the main data center. So specify that under the underlay route. Then you give the details about the node IDs, the serial number, the name of the remote leaf switches. Then you specify the OSPF information, the backbone, is it which OSPF area, what is the cost, give the details of the data plane tep information. So give the information about the tep IDs, the router IDs, and give the information about the interfaces, right, the uplink interfaces. And once you define all of this information into the template, push, and the fabric is going to be completely discovered, right? The remote leaf is going to be completely discovered. Now, this is something that a network admin does it, centrally, right? This can be done even before the remote leaf is actually attached to the fabric. So this you do it. After that, someone goes to a remote location, puts up the remote leaf switches, and it will be discovered like this. Here, you will see a different role, which is going to be a remote leaf. Here you see, except that everything is same. Remote leaf will be discovered. Yeah, question. So the question is, which version is supported with remote leaf? It is 3.1.1. The wizard is from the start. Yeah, wizard was not an afterthought. That was like a condition that we had. Wizard is from the day 0. Yeah, the question was on the wizard. Wizard is from day 0. Now the brief introduction of the vPod, right? So this is not a session on the vPod. If you want to understand the vPod in detail, the session to go is the BRKACI 2882. That's where you will learn virtual pod in detail, right? So let me give you some brief information about the vPod. Let's say you have a situation where you can't really put the ACI remote leaf, right, a physical leaf in a location. You can run ACI, you can still put the ACI policies in a software format. Like for example, you may have a bare metal cloud, right, from say IBM or Oracle, and you want to still put the ACI policies, you can use a virtual pod. And I'm going to talk about what virtual pod is, a little bit more details, but you can put a virtual pod over there which is going to push the policies for the bare metal servers, which are sitting in a bare metal cloud. You may have a brownfield environment where you cannot put ACI remote leaf. You can still use the ACI vPod to push the policies in those locations. You may have a co-location data center. You want to put consistent policy across co-location workload and the ACI main data center. You can use vPod for that purpose. And vPod will push the policies, same policies for the co-location workload as well. Now, what is vPod? There are two components to the vPod. One is the control plane, and that will be done with the virtual leaf and the virtual spine. And the other one is the data plane. And the data plane is implemented using AVE in a vPod mode. I'll come back to what is AVE in the vPod mode, but virtual leaf and virtual spine. So this is like, vPod is like a kind of a multi-pod architecture where the virtual spine is running the COOP protocol. It'll download all the information and it'll have a sync across all the spines, right? So vPod spine, virtual spine is basically helping you learn all the endpoint information. And what vLeaf does is, which is again implementing the control plane, and this is to build, the vLeaf is basically to build a more scalability. So what vLeaf does is, it downloads all the policy information from the Epic controller and pushes that policy information to the AVEs, which is implementing the policy. If we did not have this vLeaf, imagine the Epic controller has to manage so many of these AVEs, right? So how do you, so it is going to be a scalability challenge. So we build a hierarchy system where vLeaf downloads the policy from the Epic controller and pushes it to AVEs. Now, what does AVE do in a vPod mode? So the AVE in a vPod mode is going to learn all the endpoint information and do a local forwarding using VXLAN. Now, AVE in a non-vPod mode does not do a local traffic forwarding, right? Traffic goes to the leaf, and that's where the forwarding works. So this is where it is different, right? So AVE in a vPod mode is going to do a local endpoint learning. Now, since it's doing a local endpoint learning, it can actually forward the traffic directly as well. So let's take a look at a control plane for the vPod. So here, vSpine and vLeaf are going to have a IGP, BGP, COOP, all of that running, does a endpoint learning within the vPod, and the vSpine is also going to have a BGP EVPN session with all the other spines in the physical data center as well as virtual pods. So it's going to have a BGP EVPN session going to do all the endpoint learning that is going to be done by virtual spine. So when AVE needs to send a packet, it will query the virtual spine locally, And it'll ask, where do I need to go? I need to learn this endpoint information. So that can be done using the local vSpine itself. It can handle the failure as well because it is having all the endpoint information, and it is doing a BGP EVPN session with all the other vPorts and the physical spines. Then it also, the vLeaf does a TCP protocol session, the off-flex session with the Epic controller, and it downloads the policy. So this is what is the control plane for the vPort solution works, right? Now, the data plane. So with respect to the data plane, the traffic forwarding is going to be local within the pod. The traffic forwarding across the pod is going to be local as well. It's going to directly forward the traffic. To the physical pod, it is going to be a direct traffic forwarding. In terms of the failure handling, if the spine in the main data center goes down, no problem. It already had a BGP EVPN session with all the other spine. So it is not really dependent on the physical spine in the main data center, right? So that's a brief introduction about the virtual pod. And I would like to take questions about the virtual pod if you have. Yes, go ahead. Sure. So the question is, what is the minimum version that is supported for vPod? It is ACI 4.0. So the question is, can I have a local L3 out on vPod? Answer is no. I know, yeah, today it is not supported. We are planning to support that soon, but it is not yet supported today. Yeah. So the question is, can we have a local L3 out at remote leaf? Yes. You can have a local L3 out at remote leaf. It is supported from day 0. Yes. So the question is the MACsec available for remote leaf? Yes, it is available from ACI 4.0. So the question is, the traffic is going to the upstream router and coming back, right, for the inter-VRF routing. So the question is, when you have an inter-VRF routing, why do you forward the traffic to the upstream? Why can't you do a local loopback on the remote leaf itself? That's something that our ASIC is not supporting at the moment, right? There is a possibility, right? But with the current hardware, that's not supported. Yes, it will require a future hardware. Yes. Yes. So the question is, when you upgrade to a version where RL Direct is supported, will it be automatic, or do I need to do something? Actually, if you ask me, engineering preferred that it has to be automatic. But there was a downtime, right? When everyone is updated, that's when you can do it. So we cannot do that, right? So you cannot upgrade everything at the same time, right? So we are giving you a knob where when everything is updated to 4.1.2, that's when you can basically, that's when the RL direct traffic forwarding is going to happen. So there will be a knob. Now, let me conclude because I get a reminder and I don't want to hold everyone from the drinks and the dinners. So let me conclude. The conclusion is the ACI Anywhere. Essentially, what we are giving you with the solutions like multi-pod, multi-site, remote leaf, and the virtual pod is you have workload in any location, right? You can still have the ACI policies consistently across workload which are sitting in any locations, right? That's precisely is the message, right? That's precisely is the summary. It can be any type of workload. It can be bare metal. It could be VM. It could be even workload in the cloud, right? So we can support ACI policies anywhere for any type of workload, right? This is the WebEx team. I'll be looking at it very actively. I'll have your questions answered. And regarding the survey, it's important for us if I need to come back again next time with a lot more information. And please don't rate me for if you didn't like the room. That's something which is beyond my pay grade, right? I mean, I cannot control that, but your feedback is very important. Please provide that feedback. I may still have a couple of minutes, so I will still take some more questions, maybe 2, 3 more questions. Yes. So that's one of the big use case of the remote leave. The question is, can I use remote leave as a migration technology, right? So for example, I migrate and use those remote leave somewhere else, right? And then keep migrating using the remote leave. You don't have to set up another ACI fabric. You should be able to migrate directly using the remote leave switches. Remote leave to? Yeah. So your question is, can I move the remote leave switches to the main data center pod? So you start with a remote leave, and then you want to build a full pod, right? That's the question. Okay, yeah, I mean, if you want to do that, I mean, start with a remote leave and then make it a full-blown fabric. You need to just, have a layer 2 connectivity, right, with the other pod and start moving the workload like that, right? So you basically just like a multi-pod, right, solution. So it becomes like a multi-pod solution where the remote leave is attached to one of the pod, and since all of these can be L2 stretch, so you start moving the workload. Yes. Your question is when you have an Epic controller? Mm-hmm. Yeah. So the question is when you have an Epic controller, when you are building from remote leave to the main ACI data center, first shipping has happened with the Epic controller. Can I make it work? You would want to wait. So basically, the way you would do it is build a new fabric, right? So build a new fabric with the Epic controller, with the remote leaf and a spine, everything. Build a new fabric, build that new fabric in a multi-pod fashion, and then migrate the workload. You won't directly connect the remote leaf. You would not make remote leaf as a part of the whole fabric. First, you build the new fabric, migrate your workload, and then re-provision your remote leaf switches as a local leaf switches. That's how you would do it. All right. Thank you so much for your time. And enjoy your evening.